Picture yourself standing outside on flat, open ground, late in the afternoon, with the sun low and behind you. Look at your shadow lying out across the grass. It is longer than you are, quite a lot longer at that hour. Now hold that picture still and make one small comparison in your head. Not a calculation, just a feeling for the proportion. You are one height, and your shadow is about twice that, or 3 times, depending on how late it has got. Here is the part that surprises people. That proportion has almost nothing to do with you. There is a tree standing a few steps away on the same grass, and its shadow reaches out in exactly the same proportion. So does the fence post. So does a cathedral, and so does a pyramid. Every upright thing in the light, from the smallest to the largest, is casting its shadow in the same ratio at the same moment. But that ratio is not a fact about you, or the tree, or the pyramid. It is a fact about the sun. One angle up in the sky, shared out over everything standing in the field. Which means that if you can measure the small thing at your feet, you can reach the enormous thing you will never climb. Everything else is 4,000 years of people being careful with that idea. Tonight we will walk the length of it. From a slope written in ink on Egyptian papyrus, to the size of the earth worked out from a well, to the first star anyone ever measured the distance to. You do not have to follow any of it. If you are gone by the second minute, the shadows will go on, lengthening without you. Let's begin. Chapter 1. Let's stay in that field a little longer, because there is something in it worth turning over slowly. You are standing upright. Your shadow lies flat along the ground, and between the top of your head and the far tip of your shadow, there is a third line, invisible, running back up along the sunbeam that grazed you on its way past. 3 lines. You, your shadow, and the light. They close up into a triangle, and one of its corners, the one down at your feet where you meet the ground, is a square corner, a right angle. That is the shape. This whole subject lives inside. A triangle with one square corner in it. It seems like a small thing to build 4,000 years on. It turns out to be enough. Now put the tree back into the picture. The tree is taller than you, so its triangle is bigger than yours. Bigger in every direction, though. Taller upright, longer shadow, longer sunbeam, all stretched in the same proportion, like a photograph of your triangle enlarged and laid down on the grass beside it. Mathematicians call 2 shapes like that similar. It is a gentle word for a strict idea. 2 triangles are similar when their angles match, corner for corner, even if one of them is 1,000 times the size of the other. And here is the property that makes the whole subject possible. When 2 triangles are similar, every ratio inside one of them is exactly the same as the matching ratio inside the other. Say your triangle has an upright side of 1 and a shadow of 2. The tree's triangle has an upright side of 10 and a shadow of 20. 1 to 2 and 10 to 20. The numbers are entirely different. The relationship between them is identical. You can double the tree. You can shrink it to the size of a matchstick. As long as the sun stays where it is, the proportion between height and shadow does not move at all, so the size cancels out, and what is left is a pure property of the angle. Only the angle, nothing else. That is worth resting on for a moment, because it is the pivot everything turns around. Angles are things you can measure without going anywhere. You can measure an angle by standing still and looking. Distances usually make you walk, and here is a rule that hands you a distance in exchange for an angle, which is the best trade in practical mathematics. And people have been making it ever since they noticed it was on offer. Let's give the ratios their names gently, because you will meet them all night, and it is nicer to be introduced properly. Take your right-angled triangle. Pick one of the two corners that is not the square one. Say it is the corner up at the top, where the sunbeam meets your head. That corner has an angle in it. Now the three sides. There is the side directly across the triangle from your chosen corner. That one is called the opposite. There is the side running alongside it from your corner down to the square corner. That is the adjacent, which simply means the neighboring one. And there is the long slanting side that always sits across from the square corner, the longest of the three, called the hypotenuse. It is a Greek word meaning something close to stretched underneath. Three sides, so 3 ways to pair them up. The opposite, compared with the hypotenuse, is called the sine of the angle. The adjacent, compared with the hypotenuse, is called the cosine. And the opposite, compared with the adjacent, is called the tangent. That is it. That is the entire vocabulary. 3 ratios, each one a number with no units attached, each one determined completely by the angle and not at all by the size of the triangle. Every table, every survey, every satellite, every piece of the story we are going to walk through tonight comes out of those 3 comparisons. If those names feel slippery, do not chase them. They will come back around several times before morning, and they get friendlier each time. Back to the field, because there is a payoff waiting there. You want the height of the tree. You cannot climb it, and you have no way to reach the top, but you can walk. So you pace out its shadow, heel to toe, and you get, let's say, 30 paces. Then you stand your own shadow beside it and pace that 6 paces. And you know your own height because you have been measured at the doctor's. Your shadow is 6 paces for your one height. So the sun is putting down 6 paces of shadow for every unit of upright. The tree's shadow is 30 paces. 30 divided by 6 is 5. The tree is 5 times your height. You have just measured something you could not touch, using nothing but your own body and a walk across the grass. There is an old story attached to exactly this. It is told about Thales of Miletus, a Greek trader and thinker from the coast of what is now Turkey, who lived around 26 centuries ago. The story says he was in Egypt, standing at the foot of a pyramid, and that he found its height by waiting until the moment when his own shadow was exactly as long as he was tall, and then measuring the pyramid's shadow, because at that moment the 2 lengths had to match. It is a lovely story. It is worth saying plainly that we do not really know if it happened. The accounts come from writers living centuries after Thales, and they do not agree with each other about the details. What we can say is that the method is sound, that it would work, and that people in the ancient world were clearly thinking along these lines, because The pyramids themselves were built using slope ratios long before any Greek arrived to admire them. We will get to those builders shortly. For now, notice how little you needed. No instruments, no theory of light. Nothing but the observation that the sun is far enough away that its rays arrive at your patch of ground effectively parallel, so everything standing in that patch shares the same angle. The whole of trigonometry is that trade made over and over at larger and larger scale. An angle you can see exchanged for a distance you cannot walk. The tree tonight, a mountain in a few hours, a star before morning. If your eyes are closing already, that is entirely fine. There is nothing in this to keep hold of. Let it go and let it come back, and the field stays as it is. The grass, the tree, the fence post, the low sun, all those shadows lying out in the same direction, all in the same quiet proportion, lengthening by a fraction with every minute that passes, while the light goes gold and then goes. Chapter 2, the light goes, and we go back a long way before Thales of Miletus, back to a part of the world where the light was fierce and the ground was flat, and there was no stone worth speaking of, only mud. Southern Iraq, nearly 4,000 years ago. The rivers lay down silt, and people made the silt into bricks and into tablets. A tablet is a lump of damp clay you can hold in one palm, pressed with the cut end of a reed while it is still soft, then left in the sun to harden. Millions of them survive, which is a strange piece of luck. Paper burns and papyrus rots, but a clay tablet that falls into a fire simply gets better at being a tablet. Those people counted in 60s. That deserves a moment, because you are still using their 60s tonight. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a full turn, which is 6 60s. Nobody has ever come up with a reason to change it, and we have had about 4,000 years to try. Nobody is entirely certain why they chose 60. The most common explanation is that 60 divides very obligingly. It splits into halves, thirds, quarters, fifths, sixths, tenths, twelfths, 15ths, 20ths, and 30ths, without leaving anything awkward behind. If you are doing arithmetic by pressing marks into wet clay, a number that divides cleanly is a mercy. There are other explanations involving finger counting and the calendar, and honestly, we do not know. It is one of those inheritances whose reasons were lost long before anyone thought to write them down. Now, among those tablets, there is one that people argue about. It sits in a collection at Columbia University in New York, and it is catalogued as Plimpton 322. It dates from somewhere around 1800 years before the Common Era. It is a broken rectangle of clay with 4 columns of numbers on it, 15 rows deep, written in that base 60 system. The numbers are not random. They are related to right-angled triangles in a way that has been recognized since the middle of the last century. Each row corresponds to a triangle whose sides are whole numbers, the kind of triangle where the 2 short sides and the long side all come out neat. The argument is about what the tablet was for. In 2017, 2 researchers in Australia, Daniel Mansfield and Norman Wildberger, proposed that it should be read as a trigonometric table, the oldest in the world, by well over 1,000 years. Other historians of mathematics disagreed, and disagreed firmly, arguing that the tablet fits comfortably into a tradition of Babylonian problem-solving that has nothing to do with angles. We should be honest and leave that where it lies. The tablet is real. The numbers on it are real and beautiful. What was in the mind of the person who pressed them into the clay is not something we can reach. What we can say, without any argument at all, is that people were working with the proportions of right-angled triangles that early, and that they were doing it because they had things to build, which takes us west to Egypt and to a document that is much more talkative. The Rhine papyrus is a roll about 5 meters long, copied out by a scribe who gives his name as Ames around 1550 years before the Common Era. He says himself that he is copying from an older document, which is the sort of remark that makes historians sit up. Ames was not inventing. He was passing on something already old when he received it. The papyrus is a book of problems. Loaves of bread divided among workers, the volume of a granary, the slope of a pyramid. That last one is where we belong. The Egyptians had a word, sect, and it meant the horizontal run of a pyramid face for every 1 cubit that the face rises. A ratio, in other words, sideways over upwards. That is the tangent of the angle, upside down, which mathematicians would later call the cotangent, though nobody in Egypt would have recognized the word or felt they needed it. Think about why a builder needs this. You have thousands of blocks and hundreds of workers and a face of stone that must climb for 140 meters and still meet the other 3 faces exactly at the top. You cannot check the angle from the ground. What you can do is give every gang the same instruction. For every cubit you go up, come in by this much. That is a rule that survives being shouted across a work site, and it produces a straight face. And it is the reason the Great Pyramid's sides are as true as they are. So the very first appearance of these ratios in the human record is not astronomy and not geometry for its own sake. It is a construction instruction written down so that a wall would come out straight. Let's follow the sun a little further along to a much later Egypt and to a piece of reasoning I have always loved. Eratosthenes of Cyrene was the chief librarian at Alexandria around 22 centuries ago. He heard or read that in the town of Sine, far to the south, on one particular day of the year at noon, the sun stood directly overhead. You could see it reflected in the bottom of a deep well, straight down the shaft, with no shadow anywhere on the walls. At Alexandria, on the same day, at the same hour, an upright pole still cast a small shadow. Eratosthenes measured the angle of it. He found something close to 1/50th of a full turn, a little over 7 degrees, and that was enough. If the ground were flat, the sun being overhead in one town would mean it was overhead in the other. The fact that it is not overhead in both means the surface between them is curved, and the amount of the difference tells you how much of the whole curve you have crossed. 1/50th of the way round. So, the distance from Alexandria to Syene is 1/50th of the entire circumference of the earth. He had that distance from the surveyors and the camel drivers who walked it, and he multiplied. The number he got is usually given as 250,000 stadia. Whether that was close to correct depends on the length of a stadion. And there was more than one stadion in use. And the truth is, we cannot pin it down. Some reconstructions put him within a few % of the real figure. Others are more cautious. What is not in doubt is the method, which is exact and needs nothing but a stick, a shadow, and a long walk. You may let that go now. It will still be true in the morning. A well with the sun in the bottom of it, a pole in a courtyard, a man with a measuring angle, and the size of an entire planet falling out of the difference between two shadows on the same summer afternoon. Chapter 3. So far. Everything has happened on the ground. A tree, a pyramid, a pole in a courtyard. The trouble is that the ground is a small place, and the people who pushed this subject forward were not looking at the ground at all. They were looking up, tray, to hold what the night sky meant to them. No street lighting anywhere on earth, no clocks worth the name. The sky is the calendar, the compass, and the almanac all at once. And it is the only thing in their world that behaves with perfect regularity. The sun rises a little further along the horizon each morning and then turns round and comes back. The moon fills and empties. 5 bright points wander among the fixed stars, moving forward, then pausing, then sliding backwards for a while before going on again. If you want to predict any of that, you need to be able to do arithmetic with angles, not with lengths. There are no lengths in the sky. Everything you can see is a direction, and the only honest question you can ask about 2 stars is how far apart they are in angle, as seen from here. So the sky is where trigonometry actually grew up. Not in a field with a tree in it, in the dark, with the wanderers moving. Now, the Greeks who took this on did not begin with the sine. They began with something slightly different, and it is worth meeting because it explains a good deal of what comes later. Thruck a circle. Put your finger at the center and open out an angle so that 2 lines run from the center to the rim, like the hands of a clock at some particular hour. Those 2 lines cut off a piece of the rim between them, an arc. Now join the 2 ends of that arc with one straight line, cutting straight across. That straight line is called a chord, from a word meaning string, because a bow and its bowstring make exactly this shape. A short arc gives a short chord. A wider angle gives a longer one. Open the angle right out to a half turn, and the chord passes through the center and becomes the full width of the circle. Every angle has its own chord. So, if somebody sat down and worked out the chord for every angle you might reasonably want, and wrote them all in a list, then any astronomer with that list could do their work with a straight edge and some patience instead of starting again from the beginning every time. Somebody did. His name was Hipparchus of Nicaea, and he worked in the 2nd century before the Common Era, mostly on the island of Rhodes. He is a frustrating figure to talk about because almost everything he wrote is gone. One minor commentary survives. Everything else we know about him comes second-hand from people quoting him respectfully centuries later. Those sources credit him with a work in 12 books on the chords in a circle, and that is generally taken to be the first trigonometric table anyone ever made. We do not have it. We do not know exactly how he computed it. There is a reasonable reconstruction, and there are careful scholars who will tell you how much of that reconstruction is inference. But the man himself is solid. He cataloged something like 850 stars. He compared his own measurements with Babylonian records going back centuries and noticed that the whole sky had shifted very slightly against the seasons. A slow drift we now call the precession of the equinoxes, which takes about 26,000 years to come full circle. He found that by being fussy about numbers that other people had thought were settled, 3 centuries later in Alexandria, a man called Claudius Ptolemy wrote the book that carried all of this forward. It is a large book, 13 parts, written around the year 150, and its influence is difficult to overstate. It was the standard astronomical reference across the Mediterranean, then across the Islamic world, then across Europe for something close to 1400 years. We do not even call it by its Greek name anymore. We call it the Almagest, which is what happens when Arabic scholars refer to it as the greatest, and then Latin translators borrow the Arabic phrase without quite unpicking it. Inside the Almagest, before any astronomy happens, there is a table. It gives the chord of every angle from half a degree up to 180 degrees, in steps of half a degree. 360 entries, each one worked out to a precision of about 1 part in 100,000, in a circle whose radius Ptolemy sets at 60 units because he is still counting in Babylonian 60s, as everyone did. That is where our minutes and seconds come from, by the way. Ptolemy divides each degree into 60 small parts, and then divides each of those into 60 smaller parts again. In Latin, the first ones are the little parts, and the second ones are the second little parts. Minutes and seconds. The words on your bedside clock come out of a Greek astronomy textbook by way of a Latin translator's shorthand. Building that table was not simple. Some chords fall out neatly from constructions the Greeks already had. A square gives you one, a hexagon gives you another, a regular pentagon gives you a third, and takes some real work. Then Ptolemy has a result, which we now call Ptolemy's theorem, that lets him take the chords of 2 angles and find the chord of their sum and their difference. And by halving repeatedly, he can fill in the gaps. But he could not get everything. The chord of 1 single degree resisted him. There is no construction that produces it exactly. So he did something honest and rather modern. He worked out 2 chords he could construct, one just larger than the target and one just smaller, showed that his answer had to lie between them, and squeezed the gap until the difference no longer mattered at his level of precision. Sit with the labor in that for a second. Every entry computed by hand in a number system with no decimal point, no zero used the way we use it, and no shortcuts. Years of one person's life in a room in Alexandria, so that navigators and astronomers and calendar makers for the next 14 centuries could simply look the answer up. If you drift off during this part, you are in good company. Plenty of the people who owned a copy of the Almagest never read past the tables either, and the tables were the point. Somebody works patiently, through the difficult thing once and writes it down carefully, and after that it is just a list on a page, quiet and finished, waiting to be useful to a stranger who will never know their name. Chapter 4. The chord has a flaw in it, and once you see the flaw, you cannot unsee it. Go back to the circle with the arc cut out of it, and the straight chord joining the two ends. It is a handsome shape, but it is not a triangle. There is no right angle anywhere in it. The chord sits across the opening like a lid, and to get anything useful out of it, you have to keep cutting it in half in your head, over and over, because the half of a chord is the thing that actually belongs to a right-angled triangle. Somebody was going to get tired of doing that. It happened in India. Indian astronomers had inherited Greek astronomy along the trade routes, and they were doing serious work of their own with the moon and the planets. And at some point in the centuries around the year 400, they simply stopped writing down the chord and started writing down half of it instead, the half chord of half the angle, which is the sine, exactly as we use it today. It sounds like a small housekeeping decision. It is not. Every table from that point on is one step closer to the shape people actually need, and every calculation loses a fiddly halving. The sine as a thing in its own right is an Indian idea, and the whole of the rest of this night runs on it. The clearest early voice we have belongs to a man called Aryabhata. He wrote a book called the Aryabhatiya, and he tells us he finished it in the year 499 when he was 23 years old. It is a very compressed piece of work, a little over 100 verses, meant to be memorized rather than consulted. Astronomy, arithmetic, the measurement of areas, a startlingly good value for the ratio of a circle's circumference to its diameter, and an argument that the apparent turning of the stars is caused by the Earth rotating, which was not a popular position, and which he states without much fuss. And in among it, there is a sine table. It gives 24 values from a small angle up to a quarter turn, in even steps of 3 3/4 degrees. Not the values themselves, though. The differences between them, one after another, written as a string of syllables that scan as verse, so that a student could carry the entire table in their head while walking. Think about that for a moment. The table that Ptolemy filled 13 pages with, compressed into something you could recite from memory on a journey, because paper was scarce and memory was not. There is a companion function in those Indian texts that has almost vanished from modern use, and it is worth a mention because it is such a practical little object. It is called the versen. Take the arc and its chord and measure the distance from the middle of the chord out to the middle of the arc, the bulge, in other words. How far the curve stands proud of the straight line. Navigators loved it and kept it in their tables well into the 20th century, because when angles are small, the versine stays comfortably sized, while other quantities get uncomfortably close to nothing. There is a whole family of these. The versine, the cover sign, the haversine, which is simply half the versine, and which sailors used to compute distances between 2 points on the globe. They have quietly retired now, made redundant by machines that do not mind small numbers. 130 years after Aryabhata, Another mathematician called Bhaskara I was writing a commentary on that same book, and he left behind something rather charming. He gives a formula, a single, compact expression that lets you estimate the sine of any angle without a table at all. It is not exact, and he does not claim it is, but it holds to within about 1% across the entire range, which for a working astronomer in the year 629 is astonishing value for the effort involved. Nobody is certain how he arrived at it. It has the feel of a thing found by fitting, by trying shapes, until one of them sat down neatly on the numbers. Now, the word. This is my favorite piece of accidental history in the whole subject. And I should say at the front that it is the standard account, reconstructed by historians of language, and that a few of the steps are more probable than proven. In Sanskrit, the half-chord was called ja-ardha, which shortened in use to jia. The word means bowstring, which is exactly right, because that is what the shape is, a bow and the string pulled across it. Then Arabic scholars translated the Indian works. Sanskrit jia came across into Arabic as jiba, a borrowed sound rather than a real Arabic word, and here is the accident. Arabic, in that period, was commonly written without the short vowels. You wrote down the consonants, and the reader supplied the rest from context. So the written form of jiba is a little cluster of letters that could also be read as jabe, which is a real Arabic word and a common one. It means a fold or a pocket, the opening at the neck of a garment, and by extension, the curve of a bay in a coastline. Centuries later, in Spain, European translators went to work on those Arabic manuscripts, pulling Greek and Indian and Arabic learning into Latin. Gerard of Cremona was among the busiest of them, working in Toledo in the 12th century. When they reached the little cluster of consonants, they read it as the Arabic word rather than the Sanskrit one, and they translated its meaning into Latin. The Latin for a fold, a hanging curve of cloth, the bosom of a robe, a bay, is sinus. So the word you were taught in school is not a description of anything. It is a bowstring that got mistaken for the fold of a garment somewhere between India and Spain, and nobody ever went back to correct it. Every calculator on Earth has a button on it that says fold. The partner word arrived much later and much more sensibly. When you take an angle and ask what is left over before a right angle, that leftover is called the complement. The sign of the complement got shortened in English to cosine, and the person usually credited with putting it in print in that form is Edmund Gunter, an English mathematician working in the early 1600s. Tangent is Latin for touching, from a line that just grazes a circle at one point. Secant is Latin for cutting, from a line that goes right through. You are welcome to fall asleep on that. It is only vocabulary, and vocabulary keeps. A bowstring, then. Somebody in India looked at a shape that had been drawn for 800 years, cut it exactly in half, and made everything that followed simpler. The name went wandering off in another direction entirely, and came back wearing the wrong clothes. And it works just as well. Chapter 5. The bowstring traveled west, and where it landed, it found a use waiting for it. By the 9th century, Baghdad was the place where the world's books were going. Greek manuscripts came in from Byzantium, Sanskrit ones from India, Persian ones from the older empire next door, and there was a sustained effort, paid for by caliphs and by wealthy families, to translate all of it into Arabic, and then to argue with it. Ptolemy arrived, Aryabhata's tradition arrived, and they met in the same libraries. What made the difference was that this civilization had questions of its own that needed answering every single day. In every town it reached me. Consider one of them. If you are going to pray, you face Mecca, not roughly towards Mecca. The direction matters, and it is written into the architecture because every mosque has to be built with one wall square to that direction, and that wall will stand for centuries. Now, from a town in Spain, or in Central Asia, or in the Sahara, which way is Mecca? You cannot simply point south and east and hope. The earth is round, and on a round surface, the shortest path between two places curves in a way your intuition does not expect. Anyone who has looked at a flight path drawn on a flat map has met this. The plane from London to Los Angeles seems to swing absurdly far north, up over Greenland, and it is not lost. That is the straight line. Flat maps lie about it because they have to. So, the direction to Mecca is a genuine problem in the geometry of a sphere. You need the latitude and longitude of where you are and of Mecca, and then you need mathematics that can handle a triangle whose sides are not straight lines but arcs, curving over the surface of a globe. There was a second daily problem too. The times of prayer are defined by the sun, and some of them are defined by shadows. When the shadow of an upright stick has grown to a certain proportion of the stick's own height, the hour has arrived. That is a ratio of a shadow to an upright, which is to say, it is a tangent, and a timekeeper in a mosque needed tables of it for every day of the year at their own latitude. So, the shadow, which is where we started tonight, comes back as a piece of civic infrastructure. Among the people doing this work, one of the earliest we can name clearly is Muhammad ibn Musa al-Khwarizmi, working in Baghdad in the early 800s. His name is the source of the word algorithm, and the title of one of his books gives us the word algebra. He produced tables of signs, and in doing so, helped fix the Indian half-chord as the standard object rather than the Greek chord. Then, later in the same century, Muhammad ibn Jabir al-Battani, who worked in Raqqa on the Euphrates and died in the year 929, he measured with real care. His figure for the length of the solar year was off by a couple of minutes, which does not sound like much until you consider that he was working with instruments he had built himself. Nicolaus Copernicus quotes him. He turns up in European astronomy books for the next 700 years under a Latinized version of his name. For our purposes, his contribution is the shadows. He built tables of what he called the extended shadow and the reversed shadow, meaning the shadow of a vertical stick on the ground and the shadow of a horizontal peg down a wall. Those two are the cotangent and the tangent, tabulated properly for the first time we can point to. 50 years after him came Abu al-Wafa al-Bujani in Baghdad, and with him the 6 ratios finally settle into the family we still use. He treated the tangent as an object worth studying in itself, rather than a shadow you happen to measure. He named and used the secant and the cosecant, and he built a sine table of such accuracy that nobody managed to improve on it for a very long time, calculating individual values to a precision that would not be matched in Europe for centuries. He also worked on the rule that ties a triangle together on a curved surface. On flat ground, there is a beautiful relationship called the law of sines, which says that in any triangle, each side compared with the sine of the angle facing it gives the same number every time. 3 sides, 3 angles, 1 shared ratio holding them all in place. The spherical version of that law is what you need for the direction to Mecca, and for navigation, and for astronomy. Several people were closing in on it at once in that generation, and historians are careful about assigning it to any single one of them. Then, 2.5 centuries later, in the observatory at Moraga, Nasir al-Din al-Tusi, he was born in 1201 into a difficult century. The Mongol armies came through, and he ended up working for them, and out of that arrangement came an observatory with an enormous library and instruments, larger than anything built before. He wrote on astronomy, ethics, logic, and mathematics, and he wrote a book called The Treatise on the Quadrilateral, which does something none of his predecessors had done. Everyone before him had treated this material as a branch of astronomy. Signs existed to help you find where Mars would be. Al-Tusi took the whole apparatus, plane triangles and spherical triangles together, and set it out as a subject standing on its own, with its own problems and its own methods, not answerable to the sky or to anything else. That is the moment trigonometry becomes a thing rather than a technique. It has a shape you could teach to somebody who had no interest in planets whatsoever. If you are sinking now, sink. None of this needs you awake. I want to leave you with one image from the curved surface side of it, because it is a pleasant thing to hold while falling asleep. Stand at the North Pole. Walk straight south until you reach the equator. Turn 90 degrees to your left and walk along the equator for 1/4 of the way round the world. Turn 90 degrees to your left again and walk straight north. You will arrive back at the North Pole, and you will have walked a triangle with 3 sides and 3 corners, every one of those corners a right angle on flat paper that is impossible. The angles of a flat triangle always add to a half turn, no more, and there is no room in that budget for 3 right angles. But the surface of a sphere is not flat, and triangles drawn on it are allowed to be generous. That is the world those astronomers were actually working in. Not the tidy page, the outside of a ball, where every triangle carries a little extra angle, and the amount of extra tells you how much of the world you have enclosed. Chapter 6. Europe came to all of this late, and came to it through Spain. Toledo had been a Muslim city, and when it passed into Christian hands, its library stayed put, and for about a century afterwards, it was full of people bent over Arabic manuscripts, turning them into Latin. Gerard of Cremona, whom we met earlier mistranslating a bowstring, is said to have gone to Spain specifically because he wanted to read the Almagest and could not find a copy anywhere in Italy. He learned Arabic, translated the Almagest, and then, having got the taste for it, translated somewhere near 80 more books before he died. So, the material arrives in Latin, second-hand and sometimes third-hand, and Europe begins to catch up. The first European to really take hold of it was a man born in a Bavarian village in 1436 with the name Johannes Müller von Königsberg. Königsberg means King's Mountain, and being a scholar of his age, he turned that into Latin, and so he is known to everybody as Regiomontanus. He was quick. He was at university at 11 and lecturing on astronomy in his 20s, and at some point around 1464 he wrote a book called On Triangles of Every Kind, which lays out plane and spherical trigonometry as a complete self-contained system, in the way Al-Tusi had done 2 centuries before in Arabic, but now in the language European universities actually read. The book did not get printed for another 70 years in Nuremberg in 1533, long after he was dead. He died in Rome at 40, of something we cannot identify at this distance, possibly plague. Copernicus owned a copy of the printed edition and used it. Now we come to the part of the story that I find genuinely moving, and it is about the tables. Every one of these methods depends on being able to look up a sign. That is the deal. Somebody does the terrible arithmetic once, in advance, and everybody afterwards just reads it off the page. So the accuracy of European astronomy, of navigation, of surveying, of gunnery, was capped by the quality of the tables in the back of the book, which meant that improving the tables was a serious profession, and it consumed people. Georg Joachim Rheticus is the clearest example. He is best remembered for something else entirely. As a young mathematics professor, he heard rumors of an old canon in Poland with a strange theory about the Earth going round the sun, traveled hundreds of miles to meet him, stayed 2 years, and eventually talked Nicolaus Copernicus into letting his life's work go to a printer. Without Rheticus, that book might well have stayed in a drawer. But his own obsession was the tables. He made a change of definition first, and it is a quiet one that matters enormously. Everybody before him had thought of the sine as a length, a line drawn inside a circle of some chosen size. Ptolemy's circle had a radius of 60 parts. Aryabhata's had a radius of 3,438. Rheticus stopped talking about lines in a circle and started talking about ratios between the sides of a right-angled triangle, which is how you were taught it, and which frees the whole thing from having to pick a circle at all. Then he set about computing. He hired assistants. He ran them like a workshop, and he kept at it for the rest of his life. He wanted sines to 10 decimal places for every 10 seconds of arc, which is to say 6 values for every minute, 60 minutes for every degree, all the way round. He did not live to see it finished. He died in 1574, and the work sat there until one of his assistants, Valentine Otho, brought it out in 1596, more than 20 years later. The finished thing runs to something like 1,500 pages of numbers. It is a monument, and it is also a warning, because when Bartholomeus Pitiscus went carefully through it, he found errors, and had to publish corrections of his own in 1613. That same Pitiscus gave us the word. In 1595 he published a short treatise, and he needed a title for the subject. So he made one out of Greek. Trigonon, a triangle, and metron, a measure. Triangle measurement, which came out in Latin as trigonometry. The subject was well over 1,000 years old by then, and had never had a name of its own. Here is what all that arithmetic was for. Multiplication by hand is horrible. Adding two 10-digit numbers is tedious but safe. Multiplying two 10-digit numbers is a small ordeal of carrying and cross-checking, and an astronomer might do dozens of them to place one planet on one night. So somebody noticed a trick hiding inside the trigonometric identities. There is a relationship that takes the sines of two angles multiplied together and rewrites the answer as a difference between two cosines. Multiplication on one side, subtraction on the other. That means if you have good tables, you can turn any multiplication into a couple of lookups and a subtraction. You look up, you subtract, you look up again. The ordeal becomes an errand. The method was called prostapheresis, from the Greek for addition and subtraction, and it spread through the observatories of the late 1500s. It was in use at Uraniborg, the great observatory that Tycho Brahe built on a Danish island, where the most precise naked eye measurements ever made were being ground through by hand. A visiting mathematician called Paul Wittich is usually credited with bringing it there, and it was a stopgap, because in Scotland a landowner named John Napier had been chewing on the same problem for 20 years, and in 1614 he published something better, logarithms, a way of turning any multiplication at all into an addition, not just the ones that happen to look like a trigonometric identity. Here is the detail I love. The first logarithm table ever published was not a table of logarithms of ordinary numbers. It was a table of logarithms of sines. Napier built it that way because he knew exactly who his customers were and what they spent their evenings doing. You have permission to drift off here. The tables have all been checked. There is a phrase that used to be said about this, that logarithms doubled the working life of the astronomer. It sounds like flattery until you remember what the alternative was. Rooms full of people for years doing arithmetic by candlelight so that a stranger in another country could look up one number and get on with the thinking. Chapter 7. There is a problem with everything we have said so far, and the people doing the work knew about it for a very long time. A right-angled triangle has one square corner which uses up 90 degrees. That leaves 90 degrees to be shared between the other two. So the largest angle you can ever ask about inside a right-angled triangle is a little under 90, but the sky does not stop at 90 degrees. A planet goes all the way round. An angle of 140 degrees is an ordinary thing to want. 210, 340, and there is no triangle on Earth with an angle of 340 degrees in it. So, what on earth is its sign? The answer that eventually emerged is the most important idea of the night, and I want to walk into it slowly because it is the point where the subject quietly stops being about triangles at all. Draw a circle and make its radius exactly 1. 1 what does not matter, 1 meter, 1 inch, 1 anything. Because we have already seen that the ratios do not care about size. So, we may as well choose the size that makes the arithmetic disappear. Put the center of that circle at a crossing point of two lines, one running left and right, one running up and down, like the middle of a window frame. Now, put a small point on the rim of the circle, out to the right, level with the center, and start walking it round the rim, anti-clockwise, slowly. Watch two things about the point as it goes. Watch its height above the middle line, and watch how far along it is, left or right of the center line. That is all. Those two numbers, the height and the sideways position, are the sine and the cosine of the angle the point has traveled through. That is the whole definition. Not a ratio in a triangle anymore. A position of a moving point on a circle of radius 1. Start it moving. At the very beginning, the point is out to the right, level with the center. Its height is nothing at all, so the sine is nothing. Its sideways reach is the full radius, so the cosine is 1. A quarter of the way round, the point is at the top. Now the height is the full radius, so the sine is 1, and it is sitting directly above the center, so its sideways position is nothing. The cosine has fallen to nothing. Halfway round, the point is out to the left. Height is back to nothing. Sideways position is the full radius, but in the other direction, so we call the cosine minus 1. 3/4 round, the point is at the bottom. Sideways position, nothing, and the height is the full radius, downwards, so the sine is minus 1. And then it comes back to where it started, and it does the whole thing again. That minus sign is worth a second because it frightens people unnecessarily. It is not a shortfall or an error. It is only a direction. Left instead of right, below instead of above. The number tells you how far, and the sign tells you which way. And both together tell you where the point is. Now, the important part. Nothing about that walk had to stop at 90 degrees. The point simply keeps going. You can ask for the sine of 140 degrees because the point is somewhere definite at 140 degrees, up and to the left. You can ask for 340. You can ask for 1,000, and the point will have gone round nearly 3 whole times and be sitting somewhere perfectly reasonable. You can walk it backwards and get negative angles. The old ratios have not been thrown away. If you take the point somewhere in the upper right quarter and drop a straight line from it down to the middle line, you have made a right-angled triangle with the radius as its long side, the height as one short side, and the sideways distance as the other. The sine really is the opposite over the hypotenuse, exactly as before. Because the hypotenuse is 1, and dividing by 1 changes nothing, so the triangle was never the subject. The circle was. The triangle was scaffolding, useful while the building went up. And now that we can see the shape of the thing, we can take the scaffolding down. This is also where a great deal of the tidiness comes from. Look at the sine and the cosine again as the point travels. They do exactly the same thing. Both start somewhere, rise to 1, fall to minus 1, come back. The only difference is that the cosine is doing it a quarter turn earlier. Cosine is sine with a head start. They are one motion, watched from 2 directions, which is why the identities connecting them are so numerous and so friendly. The tangent fits in as well, and its home on the circle is rather elegant. Take the point on the rim, draw a straight line from the center out through it, and keep going. Then stand a vertical line up at the right-hand edge of the circle, touching it at exactly one spot. Where those two lines meet, the height of the meeting point above the middle line is the tangent, touching from the Latin, the line that grazes the circle, and it explains something that puzzles students. As the angle approaches 90 degrees, the line from the center swings towards vertical, and a vertical line never meets that upright at all. So the tangent grows without limit and then has nowhere to be. It is not misbehaving. It has simply run off the edge of a diagram that ends. The person who finished this shift more than anyone was Leonhard Euler, working in the 1700s in Basel, then St. Petersburg, then Berlin, then St. Petersburg again. In a book of 1748, he set the radius at 1 as a matter of course, and he treated the sine and the cosine as functions, not lengths, not lines, not entries in a table, machines that take a number in and give a number back. Feed in an angle, receive a height. Feed in any number at all, receive a height. That sounds like bookkeeping. It is the door into everything after. Once the sine is a function of a plain number rather than a picture of a triangle, it can be added to other functions, differentiated, expanded into an infinite series, and dropped into equations that have nothing to do with geometry. There is nothing to hold on to here. Let the point keep walking without you, and it does keep walking, round and round, at whatever speed you like, its height rising and falling and rising again, never getting anywhere, never stopping, tracing the same two numbers over and over for as long as anyone cares to watch. Chapter 8. Let's slow right down, because the last stretch was the steepest part of the night, and there is no hurry now. The point is still going round its circle. We are going to change nothing about it. We are only going to change how we describe how far it has gone, because there is something slightly odd about degrees, and it has been sitting there unmentioned since the beginning. Where does 360 come from? We touched on it earlier. It is Babylonian. It is 6 of their 60s. The usual explanation is that a year has roughly 360 days. So the sun appears to shift by about 1 of these units against the stars each day, which is a pleasant way for the number to have been born. It also divides beautifully. You can cut 360 into halves, thirds, quarters, fifths, sixths, eighths, ninths, tenths, twelfths, and more. And every time you get a whole number back. For anyone dividing up a circle by hand, that is a kindness. But it is a convention, not a fact about the world. There is nothing in a circle that insists on 360. You can tell it is a convention because people have tried to replace it. During the French Revolution, in the same enthusiasm that gave us the meter and the kilogram, somebody proposed dividing a right angle into 100 units instead, making 400 to the full turn. It is called the Gradian. It never really caught on, though it lingers in some surveying instruments to this day, and your calculator very likely still has a setting for it that you have never once used on purpose. So, if the number is arbitrary, is there a natural way to measure an angle? a way that comes out of the circle itself rather than out of a Mesopotamian calendar. There is, and it is the loveliest small idea in the subject. Take your circle and take a piece of string exactly as long as the radius. Lay one end of the string on the rim and bend the string round to follow the curve. It will reach a certain distance round, and then it stops. Now draw 2 lines from the center out to the 2 ends of your bent string. The angle between them is 1 radian. That is the whole definition. 1 radian is the angle you get when the piece of the rim you have walked along is exactly as long as the radius. You have measured the circle using its own body. No calendar, no 60s, no committee. How big is it? A little under 60 degrees, about 57 and a bit if you want the number. And how many of them go round a full circle? Well, that is asking how many radius lengths of string fit around the whole rim, which is asking for the circumference in units of the radius. And that number is 2 pi, a little over 6 1/4, which means a full turn is 2 pi radians. A half turn is pi. A right angle is pi over 2. I know that seems like a step backwards. We have swapped a friendly round number for one that never ends and never repeats. 360 is a comfortable thing to say out loud. 6.28 and onwards forever is not. Here is why it is worth it. The first reason is immediate and practical. If you know the radius of a circle and you know the angle in radians, then the length of the arc is simply the radius multiplied by the angle. That is it. No conversion factor, no fiddly constant to remember. Ask the same question in degrees and you have to drag pi over 180 around with you all afternoon. So anything that involves a wheel or a curve or a distance along the surface of the earth becomes one clean multiplication. The second reason is deeper, and it is the one that actually decides the matter. Take a very small angle, very small, and compare the sine of that angle with the angle itself measured in radians. They are almost exactly the same number. The smaller the angle, the better the agreement. At 1/100th of a radian, the sine agrees with the angle to about 5 decimal places. You can see why from the picture. For a tiny slice of the circle, the little arc along the rim and the little vertical drop are nearly the same short line, because the curve has not had room to bend yet. So the arc and the sine converge. That single fact is why physics and engineering use radians and never argue about it. When you work out how a pendulum swings, or how a beam bends, or how light bends round an edge, the calculation gets you to the sine of a small angle, and in radians you can simply replace it with the angle and carry on. Whole subjects rest on that substitution. Choose degrees and a stray constant crawls into every formula you write for the rest of your life. The idea is older than the word. Roger Coates, an English mathematician who worked with Isaac Newton and died very young in 1716, was using angle measure of exactly this kind, and he understood what it was good for. His work on it was published after his death. The word itself came much later and rather casually. It appears in print in 1873 in examination papers set by James Thomson, a professor at Queen's College in Belfast. His younger brother was William Thomson, who is better known by the title he was later given, and who was already using the same idea in his own work. There is a suggestion that the word had been used informally around the college for a few years before it was printed. The details are thin, as they often are, for words that grow out of conversation rather than out of a book. You may let all of that slide. There is nothing here to keep. I like this idea more than almost anything else in the subject, and I think it is because of what it says about measurement generally. You can measure a thing with a unit you brought with you. A ruler, a calendar, a decision made 4,000 years ago by people who liked the number 60. That works, and there is nothing wrong with it, and most of the time, it is more convenient. Or you can measure a thing with a part of itself. Ask how far round the rim you have gone, and answer in radius. Length, then the answer belongs to the circle, and not to you, and every circle in the universe agrees on it. The point on the rim is still going. It does not know or care which units we are counting in. It rises, and it falls, and it comes round again, and the string laid along the rim behind it keeps growing, one radius length at a time. Chapter 9. Keep the point going round its circle, and let's do one simple thing to it. Crouch down until your eye is level with the middle of the circle so that you are looking at it edge on. The circle flattens to a line, and the point, which was going round, now appears to be doing something quite different. It slides out to the right, slows, stops, comes back through the middle, slides out to the left, slows, stops, and comes back again. Over and over, at a steady beat, never quite the same speed twice, fast through the middle, slow at the ends. Nothing about the point has changed. It is still traveling round at a constant rate. You have only removed one dimension by lowering your head, and the going round has turned into a going back and forth. Now let's draw what it does. Imagine the point is holding a pen, and the pen touches a long strip of paper, and the paper is being pulled steadily sideways underneath it, while the point rises and falls. What gets drawn is a smooth curve, up to a rounded crest, down through the middle, on to a rounded trough, back up through the middle, on to the next crest. Even, patient, endlessly repeating. It is not a series of arches, and it is not a zigzag, but something softer than either, with no corners in it anywhere. That is a sine wave, and you have been looking at it your whole life. Here is what makes it more than a nice shape. That curve is not just a picture of a circle unrolled. It is the shape of an enormous number of things that actually move, and there is a good reason why. Think about a child on a swing. Push them once and let them go. They swing forward, slow, hang for an instant at the top, come back, rush through the bottom, rise on the other side, hang, and return. Fast through the middle, slow at the ends, exactly like the point seen edge on. Why does it do that? Because of the shape of the force acting on it. When the swing is far out to one side, gravity is pulling it strongly back towards the middle. When it is near the middle, the pull is gentle. The further it strays, the harder it is drawn back, and roughly in proportion. That is the recipe. Anything pulled back towards a resting place, with a strength proportional to how far it has wandered, will move in exactly this way. Physicists call it simple harmonic motion. And once you have the recipe, you start finding it everywhere. A weight bouncing on a spring. Stretch a spring, and it pulls back, and it pulls back twice as hard when you stretch it twice as far. That relationship was written down by Robert Hooke in the 1600s, and it is the reason a mass on a spring bobs up and down in a sine wave. A guitar string pulled sideways and released. The tension hauls it back towards straight, harder the further you have pulled. Water sloshing in a bay, a floating buoy lifting on the swell. The air in an organ pipe, the balance wheel in a mechanical watch, turning one way and then the other, ticking off the seconds by refusing to settle. There is a small honesty I owe you here, and it connects to the last stretch rather nicely. A swinging pendulum is not perfectly a sine wave. If you pull it far out to the side and let go, the motion is a little different in shape, and the swing takes slightly longer than it would for a small one. It only becomes a true sine wave in the limit of small swings, and the reason is exactly the fact we met earlier. For small angles, the sine of the angle and the angle itself are effectively the same number. And that is precisely the step that turns the pendulum's equation into the simple one. Christian Huygens knew this in the 1650s when he built the first pendulum clocks. He worried at it and designed curved metal cheeks to hang the pendulum from, so that the bob would follow a slightly different path and keep perfect time at any amplitude. The idea was correct, and the mechanism was a nuisance in practice, and clockmakers mostly solved it by keeping the swing small. So the sine wave is an idealization that reality leans towards, which is the usual arrangement. Now let's name the 4 things you can change about such a wave, because they are the vocabulary for the rest of the night, and each of them is something you can feel. The first is amplitude. How far the point strays from the middle. On the circle, that is simply the radius. In sound, it is how loud. In light, how bright. In a swing, how high. The second is period. How long one complete cycle takes. From crest to crest. The third is frequency, which is the same information turned inside out. How many complete cycles happen in a second? A short period means a high frequency, and the two multiply together to give one. The fourth is phase, where in the cycle, the wave happens to be when you start watching. 2 waves can be identical in every other respect and simply be out of step, one arriving at its crest while the other is still climbing. Phase is the difference between them, and it turns out to matter enormously. That is the whole vocabulary. Amplitude, period, frequency, phase. How big, how long, how often, how out of step. You do not need to keep any of that. It will still be here in the morning, or it will not, and either is fine. Here is where it leaves us. We started with a shadow on a field and a ratio in a triangle, invented so that people could measure a pyramid and predict a planet, and it has quietly turned into the natural description of anything that repeats, anything that swings, bobs, oscillates, orbits, vibrates, or hums. The bowstring became a wave. Nobody planned that. Somewhere in this room, right now, air is carrying pressure back and forth in exactly this pattern, and so is the alternating current in the wire behind the wall, and so is the light from any screen that is still on. Small circles turning, all of them, seen edge on, rising and falling and coming round again. Chapter 10. If you ever sat an exam in this subject, there is a good chance the thing you remember with least affection is the list of identities, a page of them, printed in small type at the front of the paper, formulas connecting sines to cosines, angles to double angles, sums to products. They arrive looking like a set of rules handed down by somebody who enjoyed making you memorize things. They are not that. Every one of them was found because somebody needed it to get a job done, and several of them we have already met tonight without knowing their names. So let's take a gentle walk through the important ones and see where they come from. The first is the one everything else leans on, and you can see it without any algebra at all. Go back to the point on the circle of radius 1. Take it somewhere up and to the right and drop a line straight down from it to the middle line. You have a right-angled triangle. Its upright side is the sine, its base is the cosine, and its long slanting side is the radius, which is 1, because we chose it to be. Now apply the oldest theorem in the book, the one attributed to Pythagoras of Samos. In any right-angled triangle, the square of the long side equals the squares of the two short sides added together. So, the sine squared plus the cosine squared equals 1. That is the identity people call the Pythagorean identity, and it is true for every angle you can name. Not approximately, not usually, always, all the way round the circle, for negative angles and for angles of 10,000 degrees. And notice what it actually says. It says the point is on the circle. That is all. It is the equation of the circle itself, written in a different alphabet. The most famous identity in trigonometry is simply the statement that the point never falls off the rim. I find that quietly satisfying. A rule that looks like a burden turns out to be a description of a shape. Now the harder family, the addition formulas. The question they answer is obvious once you ask it. You know the sine of one angle. You know the sine of another. What is the sine of the two angles put together? The tempting answer is that you add them. The tempting answer is wrong, and you can check it in your head. The sine of 90 degrees is 1. So if adding worked, the sine of 90 plus 90, which is 180 degrees, would be 2. But we walked the point round earlier and found that at 180 degrees, it is sitting flat on the middle line, so its sine is nothing at all. The real relationship is a little more generous. The sine of two angles added together is the sine of the first times the cosine of the second, plus the cosine of the first times the sine of the second. Both quantities appear crossed over, and the answer comes out right every time. There is a matching one for the cosine, which is the same shape with a subtraction in it, and the pairs not crossed over. These are the workhorses. Everything else on that exam paper comes out of them. Set the two angles equal to each other, and you get the double angle formulas. Halve them, and you get the half angle formulas, which is how the old table makers filled in the gaps between the entries they could construct exactly. And they are ancient. Claudius Ptolemy had a version of them in the Almagest, though he wrote it in the language of chords rather than signs. and in a geometrical form. His version is a statement about a four-sided figure with all four corners sitting on a circle. It says that if you multiply the lengths of the two diagonals, you get exactly the same answer as multiplying the two pairs of opposite sides and adding those together. That is Ptolemy's theorem, and it is a beautiful piece of pure geometry in its own right, and it is also precisely the addition formula in disguise. He needed it to fill in his table, and he proved it first, and everything else in that 13-part book stands on top of it. Then there is the family that saved the most human hours, and it is the one that closes a loop we opened earlier. Take the addition formula for the cosine and the subtraction formula for the cosine and put them side by side. Some terms match and some do not, and if you subtract one from the other, half the mess cancels out. What you are left with is this: the sine of one angle multiplied by the sine of another equals half of the difference between two cosines, the cosine of the two angles subtracted, and the cosine of the two angles added. Ride that once more if you like, and then let it go, because the point is not the formula. The point is which operation is on which side. On the left there is a multiplication. On the right there is a subtraction and two lookups in a table. That is prostaphoresis. That is the trick the astronomers at Tycho Brahe's observatory used to grind through their arithmetic before logarithms existed. This little identity, sitting quietly on the formula sheet, was once a labor-saving machine that turned an hour of miserable long multiplication into 2 glances at a book and a piece of subtraction you could do standing up. They are all like that if you look. Every identity on that page is a shortcut that somebody wanted badly this Eve now, if you would like to. None of this will be tested. And there is one more thing worth saying about identities in general, which is about the word. An equation is a question. It asks which values make a statement true, and usually only a few do. An identity makes no such demand. It is true for every value, everywhere, without exception or condition. You cannot solve it because there is nothing left to find out. It is a description of how the world is put together, written in the only form that leaves no room for argument. The sine squared and the cosine squared, added, come to 1. They did on that field in the afternoon light, and they do in this room in the dark, and they will keep doing it all night, whether anyone is watching or not. Chapter 11. The sine wave is a very particular shape. Smooth, rounded, endlessly repeating. The same every time. Almost nothing in the world looks like that. A heartbeat traced on a monitor has sharp spikes in it. A note from a violin repeats, but its shape is jagged and complicated. The waveform of your own voice, saying a single vowel, is a busy mess that repeats a couple of 100 times a second and looks nothing like a smooth curve. The rise and fall of the tide is uneven, higher some fortnights than others, different in every harbor on the coast. So the sine wave seems like a special case. Lovely, tidy, and rare. The discovery that turns everything upside down is this: every one of those shapes is made of sine waves, not resembles, made of. Add enough of them together, with the right sizes and the right timings, and any repeating shape at all will come out. The man who pushed that idea into the world was called Jean-Baptiste Joseph Fourier. He had an eventful life for a mathematician. Born in central France in 1768, orphaned at 10, educated by monks. He was caught up in the Revolution and arrested during the Terror and came fairly close to the guillotine. Then he went to Egypt with Napoleon Bonaparte's expedition as a scientific member, spent 3 years there running the institute in Cairo, and came home to be made prefect of a district in the Alps, where he was responsible for road building and for draining marshes. And in among the administration, he was thinking about heat, not a glamorous problem. Take a metal bar, heat one end, and ask how the warmth spreads along it over time. Or take a ring of iron, heat part of it, and ask what happens as the heat evens itself out. Practical, dull, and completely resistant to the mathematics of the day. Fourier's insight was to change what he was solving for. He could work out how heat behaves if the starting temperature along the bar happens to be a smooth, sine-shaped ripple. That case is tractable. It just fades away gently, keeping its shape. But nobody's bar starts out with a sine-shaped temperature. Real bars start out hot at one end and cold at the other, with a sharp corner in the middle where you touched the flame. So Fourier made his claim. Take whatever starting shape you actually have, however awkward, however sharp-cornered, and write it as a sum of sine waves. Then solve the easy problem for each of those waves separately, since each of them just fades quietly on its own. Then add all the answers back up. Whatever it was you could not solve, you have now solved by taking it to pieces. He presented this in 1807 to the mathematical establishment in Paris, and they did not care for it. Joseph Louis Lagrange, who was one of the finest mathematicians alive, and had thought hard about vibrating strings himself, objected, and his objection was not unreasonable. A sum of smooth curves that produces a shape with a sharp corner in it sounded like getting something for nothing. Where does the corner come from if every ingredient is round? The answer is that it comes from infinity and from cancellation. Add 2 sine waves and you get a wobble. Add 10, chosen carefully, and you get something with steep sides and a flattish top. Add 100 and the sides get steeper. The corner is never quite there at any finite stage. It is what the sum is heading towards. Fourier was right about the substance and loose about the proof, and the mathematicians who came after spent the better part of a century tightening it up, working out exactly which shapes can be built this way, and in exactly what sense the infinite sum arrives. Peter Gustav Lejeune Dirichlet gave the first careful conditions in 1829. That tidying up work turned out to be one of the most productive arguments in the history of mathematics, and whole fields grew out of it. Fourier's book came out in 1822. The claim held. Now, let me give you the picture that made it real for people, because it involves a machine you can imagine touching. The tides are a genuine problem. Ports need to know when there will be enough water under a ship, and the pattern in any given harbor is a tangle, shaped by the moon, the sun, the shape of the coastline, and the depth of the seabed. It repeats, but not simply. In the 1870s, William Thomson, a Scottish physicist better known by the title Lord Kelvin, built a machine to predict it. Inside were a set of pulleys and gears, each one turning at a different steady rate, each one representing one sine wave in the sum. Every wheel contributed its own rise and fall to a wire threaded through the whole assembly, and the wire's total movement was the sum of all of them. A pen on the end of the wire drew the tide curve on a moving roll of paper. You turned a crank. The machine added up sine waves mechanically, faster than any human could, and out came next year's tides for a particular harbor, drawn in ink. Those machines were used for the best part of a century. There were versions still in service planning the Normandy landings. And here is where it lands tonight. The music you have listened to today was stored as a list of sine waves. When audio is compressed to make a file small, the machine takes short slices of sound, works out which sine waves it is built from, throws away the ones your ear will not miss, and keeps the recipe rather than the sound. The photographs on your phone are stored the same way. The image is cut into small blocks. Each block is expressed as a sum of ripples, and the faint ones are discarded. What is saved is not a picture. It is a set of instructions for rebuilding one out of waves. The same mathematics reads the tremors from an earthquake, tunes a radio, cleans up a medical scan, and lets a phone recognize a spoken word. You can stop here. It is all handled. Fourier was trying to work out how a hot iron bar cools down. He noticed that a complicated thing can be taken apart into simple things, and that the simple thing worth taking it apart into is the shape a point makes going round a circle. Which was the bowstring? Which was the shadow on the field? Nobody could have seen that coming from where we started, and there is no reason it had to be true. It just is. Chapter 12. Let's come down out of the abstract and put our feet on the ground again, because there is a story here about people walking, and it is one of the great quiet achievements of the last few hundred years. The problem is simple to state. How do you make an accurate map of a country? Measuring distance by walking it is hopeless over any real scale. Chains stretch, ground rises and falls, and rivers get in the way. Errors accumulate with every step, and after 100 miles, you have no idea how wrong you are. But angles are different. An angle can be measured very precisely from a fixed spot, with a good instrument and a steady hand, and the measurement does not degrade with distance. You can sight a church spire 20 miles off and read the bearing to a fraction of a second of arc. So here is the method, and it is beautiful. You measure one length, exactly one. You choose the flattest, most cooperative stretch of ground you can find, a few miles of it, and you measure that baseline with obsessive care over weeks, with rods laid end to end, and corrections applied for temperature and for the sag of the chain. Then you never measure a length again. You pick a third point, off to the side, some prominent thing you can see from both ends of your baseline. A hilltop, a spire, a signal tower you have built for the purpose. From each end of the baseline, you measure the angle to it. Now you have one side and two angles of a triangle, and trigonometry hands you the other two sides without anybody walking anywhere. And now you have three sides you know. Any one of them can be the baseline for the next triangle. So you throw another triangle off the far edge and another off that, and you keep going. A chain of triangles crawling across the landscape, each one built on the calculated sides of the last, one careful measurement at the beginning, and then angles all the way to the other end of the country. Willebrord Snellius did an early version of this in the Netherlands from about 1615, measuring from Alkmaar down to Bergen op Zoom, with a chain of triangles between church towers, which is exactly the right country for it, being flat and well supplied with spires. He was trying to find the size of the earth. Then France took it up on a national scale, and one family took it over. Giovanni Domenico Cassini was an Italian astronomer brought to Paris to run the new observatory. His son continued the work, and his grandson, César-François Cassini-Thierry, turned it into a full survey of the kingdom, and his great-grandson finished it. 4 generations, more than a century, triangles from the Channel to the Mediterranean. Along the way, they discovered that France was smaller than everybody had thought. The old maps were generous. The coastline came in, the territory shrank on paper, and there is a remark attributed to the king about having lost more ground to his astronomers than to any of his enemies. It is a good line. It is also the sort of good line that gets attached to kings afterwards, so hold it loosely. Then there is India, which is the version of this story that stays with me. The Great Trigonometrical Survey began in 1802 under William Lambton, an officer in the British Army in India, and the ambition of it was extraordinary. He proposed to run a chain of triangles up the entire length of the subcontinent, from the southern tip all the way to the Himalayas, and to do it to a standard of accuracy nobody had attempted over that distance. The central instrument was a theodolite, the size of a piece of furniture. It weighed around half a ton. It had to be carried by a dozen men, hauled up hills, and winched to the top of towers and temples, and when the ground was too flat and too hazy, they built stone platforms to lift it above the dust. The work took decades. Malaria killed surveyors in numbers. Tigers were a genuine hazard in the forests. Lambton himself died in the field in 1823, still working, and the survey passed to George Everest, who ran it for the next 20 years and drove it north. By the middle of the century, the chain had reached the plains below the Himalayas, and the surveyors began measuring angles to the peaks on the northern horizon, 100 miles away and more. That is delicate work. Light bends as it passes through air of different densities, so a distant summit is not quite where it appears to be, and the correction depends on the weather. And there is a stranger complication. The Himalayas contain so much rock that they pull sideways on a plumb line. So the surveyor's idea of straight down was itself being tugged off true by the very mountains they were measuring. They had to work out how much and allow for it. The peaks were given numbers as they were catalogued. One of them was Peak 15. The story that is usually told is that in 1852, the chief computer of the survey, a Bengali mathematician named Radhanath Sikdar, finished working through the observations and realized that Peak 15 was the highest mountain on Earth The story includes him hurrying in to announce it. How much of that scene is accurate is not certain, and historians differ on the details, but Sikdar's role in the computations is well established, and he was by every account exceptionally good at the work. The figures were checked and rechecked for years. In 1856, the Surveyor General, Andrew Scott Waugh, published the height as 29,002 feet. Modern measurement, with satellites and with people standing on the summit holding receivers, puts it about 30 feet higher, which, for a number arrived at by measuring angles from 100 miles away, through shimmering air, with a brass instrument using tables computed by hand, is a remarkable result. Waugh named the mountain after his predecessor. George Everest objected on the grounds that the survey's own policy was to use local names wherever they could be found, and he pointed out that his name could not be written easily in Hindi. He was overruled. He never saw the mountain. You are allowed to drift off now. The measuring is finished. That is the shadow on the field again, and nothing else. A ratio inside a triangle applied a few thousand times in a row by people carrying half a ton of brass up hills for 30 years until a continent had been described to within a few feet, and the highest place on the planet had a number attached to it. Chapter 13. Now take the same triangle and point it upwards where there is nothing to walk on at all. Hold your thumb up at arm's length. Close your left eye and look at it with your right. Then swap the thumb, jump sideways against whatever is behind it. Nothing moved. Your thumb stayed put, and so did the wall. All that changed was the place you were looking from, and the shift you see is called parallax. Bring your thumb closer, and the jump gets bigger. Hold it further away, and the jump gets smaller. So the size of the jump tells you the distance, and if you know how far apart your two eyes are, you can work out how far away your thumb is without reaching for it. That is the last triangle of the night, and it is the one that measured the universe. The baseline is the distance between the two places you look from. The angle is the shift you see, and the further away the thing is, the smaller that shift becomes, which means the whole business is a race between the length of your baseline and the patience of your instruments. The first person we know of who tried this in earnest was Aristarchus of Samos. Working in the 3rd century before the Common Era, his idea was elegant. When the moon is exactly half lit, the sun, the moon, and the earth must form a right-angled triangle with the square corner at the moon. So if you can measure the angle between the moon and the sun in the sky, at that exact moment, the shape of the triangle is fixed, and the ratio of the distances falls out. He measured that angle as 87 degrees, and concluded that the sun is around 20 times further away than the moon. The true angle is a shade under 89 degrees and 52 minutes, and the sun is about 400 times further. He was wrong by a very large factor. But look at what he was actually attempting, with no telescope, no clock worth the name, and no way of knowing precisely when the moon was exactly half lit. The geometry is perfect, and the reasoning behind it is sound. The instrument simply was not up to the job. That gap between a sound method and an inadequate measurement is where a great deal of the history of science lies, and Aristarchus is on the right side of it. The moon itself was tackled successfully. Because it is close, its parallax is generous. Observers in two different places see it against slightly different stars, and from that shift, Hipparchus of Nicaea worked out that the moon is around 60 Earth radii away, which is very nearly right. The sun was much harder, and it took until 1672. Giovanni Domenico Cassini, at the observatory in Paris, arranged for a colleague named Jean Richer to sail to Cayenne in South America, and for both of them to measure the position of Mars against the background stars on the same nights when Mars was at its closest. Two observers, one planet, several thousand miles of baseline between them. The shift was tiny, and they found it. From that, with the known proportions of the solar system, they worked out the distance from the Earth to the Sun, and their answer was within about 1/10 of the modern value. The first honest measurement of the size of the solar system, made by two men on two continents looking at the same red dot. The stars were another matter entirely. Here is the thing that had been bothering astronomers for 2,000 years. If the Earth really goes round the Sun, then in 6 months we move to the opposite side of our orbit, an enormous baseline, hundreds of millions of kilometers across. Over that journey, the nearer stars ought to shift against the further ones. Your thumb ought to jump. No body could see it. Not with the naked eye, and not with the early telescopes either, and not with the finest instruments the 17th century could build. There were only two ways out. Either the Earth stands still, or the stars are so far away that even that colossal baseline is not enough. The second explanation was correct, and accepting it meant accepting distances that people found genuinely difficult to hold in mind. The measurement finally came in 1838. Friedrich Wilhelm Bessel, a German astronomer who had begun life as an accounting clerk and taught himself the mathematics in the evenings, chose a faint and unremarkable star in the constellation of the Swan, known as 61 Cygni. He chose it because it moves noticeably against its neighbors, which suggested it might be close. He watched it for 18 months with a very fine instrument, and he found the shift. About 1/3 of a second of arc. A second of arc is 1/3600th of a degree. To picture 1/3 of one, imagine looking at a coin held up 10 miles away and noticing that it has moved by its own width. That measurement put the star at a distance of a little over 10 light years. The modern figure is around 11. Two other astronomers, Thomas Henderson and Friedrich Georg Wilhelm von Struve, were closing in on the same result for other stars at almost the same moment, which is how these things usually happen. The unit of distance that came out of this work is the parsec, a word coined in 1913 by the British astronomer Herbert Hall Turner. It is the distance at which a star would show a parallax of exactly 1 second of arc, and it comes to a bit over 3 light years. Every time you hear a distance in parsecs, you are hearing a shadow of that little triangle. The work has not stopped. A European spacecraft called Gaia spent years spinning slowly in the dark, doing nothing but measuring the parallax of stars and it has now done this for well over 1 billion of them, and everything further away rests on it. The whole ladder of cosmic distance, out to galaxies and beyond, is calibrated at the bottom rung by parallax. If the triangles were wrong, the size of the universe would be wrong. Nothing needs you for any of this. Let it carry on. A thumb held up at arm's length, one eye and then the other. Somebody pointed that at the sky, waited half a year for the Earth to carry them to the far side of its orbit, looked again, and found the whole thing had shifted by the width of a coin 10 miles off. And that was enough. Chapter 14. Let's come back down from the stars and back into this room and finish by looking around. Because the odd thing about trigonometry is how thoroughly it disappeared. Nobody uses tables anymore. Nobody in ordinary life sights a church spire through a brass instrument. The subject has the reputation of being finished, an old thing that got solved and put away. It did not go anywhere. It went underneath. Start with any screen you have looked at today. Every time something on it turned, rotated, tilted, or swung round a corner, a machine calculated a sine and a cosine to work out where each point should go. That is what a rotation is, arithmetically. Take a position, feed the angle into those two functions, and combine. A phone doing something as small as spinning an image when you tip it sideways is walking a point round a circle thousands of times a second without any fuss at all. Anything with 3 dimensions in it is doing far more. A camera angle in a game, the way light falls on a curved surface, the direction a character is facing. All of it is angles turned into positions, over and over faster than you can perceive. Then, look at the wall. The electricity coming out of a socket in your house alternates. It does not flow steadily in one direction. It rises, falls, reverses, and comes back 50 or 60 times a second, depending on which country you are lying down in. And the shape it traces is a sine wave. Not approximately, exactly, by design. The reason is lovely and simple. In a power station, a coil of wire is spinning inside a magnetic field, going round and round. The voltage it generates depends on the angle of the coil as it turns, which means the electricity in your walls is the height of a point going round a circle, and the circle is a real physical thing, a shaft turning in a turbine hall somewhere, driven by steam or falling water or wind. The socket is a circle in disguise. The whole grid is sound, too. Any electronic instrument that makes a note is generating waves and adding them, and the simplest starting point is a pure sine. Add a few in the right proportions, and you get warmth or brightness or something like a reed or a bell. That is Fourier's idea running backwards, building a complicated sound out of simple ingredients rather than taking one apart. And when you play a recorded song, the file on the device is a set of instructions describing which waves to add together, in which proportions. William Thomson's Tide machine did that with brass pulleys and wire, one harbor at a time, cranked by hand. The thing in your pocket does the same arithmetic tens of thousands of times a second for whatever you ask it to play, and it does it silently. Now, satellite navigation, which deserves an honest word. It is often said that your phone finds you by triangulation. That is not quite what happens, And the real answer is more interesting anyway. The satellites do not measure angles. Each one broadcasts a signal saying what time it is and where it is, and your receiver compares that time against its own, works out how long the signal took to arrive, and multiplies by the speed of light to get a distance. Do that with 4 satellites, and the distances alone are enough to fix a point in space. But a point in space is not an address. To turn that position into a latitude and a longitude, into a place on the curved surface of the Earth with a road name attached to it, you need the mathematics of triangles on a sphere, which is the same mathematics that Nasir al-Din al-Tusi set out as a subject in its own right, and that people used for centuries to find the direction of Mecca from a courtyard in Spain. The problem has not changed. Where am I? On the surface of a ball, and which way should I face? There is more, quietly. Medical scanners rebuild a picture of the inside of a body out of waves. Seismologists read the shape of the planet's interior from the arrival times and angles of earthquake waves. Bridges and buildings are checked against the frequencies at which they would prefer to sway. Radio, sonar, tide tables, weather models, the shape of a lens. You may sleep through all of it. It runs perfectly well, unattended, and then there is you. Your chest is rising and falling as you lie here. It has been doing it since before you were born, and it will do it all night without asking permission. And if you drew that motion on a strip of paper, you would get a curve that a mathematician would recognize immediately. Not a perfect one, a real one with variations in it. Faster when you dream and slower now. Your heart does it too, in its own rhythm, and a doctor reading a trace of it is reading a repeating waveform and looking at its shape. You have a rhythm of about a day in you that decides when you get sleepy, and it is drifting you downwards right now. There is a rhythm of about a month in the tides outside, wherever your nearest coast is, and the water is rising or falling against a harbor wall as you lie here. And a rhythm of a year in the tilt of the planet, which is why the sun sits at a different angle in the afternoon in June than it does in December, and why the shadow we started with is a different length in every season. All of it is the same shape. A thing going round, seen from the side. So come back, all the way back, past the spacecraft counting stars, and the surveyors on their towers, and the tide machine turning in its case, and Fourier in a cold French office thinking about a hot iron bar, past the pendulum, and the point walking round its circle, and the bowstring that got mistaken for the fold of a garment, past the observatory at Margay, and the table in Alexandria, and the scry bombs writing down a slope so that a wall would come out straight. Come back to the field in the late afternoon with the sun low. You are standing there, and your shadow is lying out across the grass longer than you are. The tree beside you is casting its own in exactly the same proportion, and so is the fence post, and so is everything else standing in that light. Nobody has to measure it. Nobody has to write anything down. The proportion is simply there, the way it has been there every afternoon, since long before there was anyone in the field to notice, and it will go on being there tomorrow, whether or not you are awake to check. Let the light go gold, let the shadows go long, and then longer, and then let them go entirely. Das leave well. Good night.